Hey, welcome back to Math with Patrick. Today's October 28th, and we're solving problem 301 from the Daily Epsilon calendar. And the answer today should be 28 because that's today's date. So we have a cyclic group of order 4004, and it's generated by A. Okay, pause, a little bit of vocab. A group is like a mathematical object or just a thing, essentially, that has a collection of other things, usually numbers. So let's just say like 0, 1, 2, 3, for example. And then a rule to combine parts or elements of my group. So let's say here my rule is going to be addition, for example. So here I could do like 0 plus 1. I'm combining those two, and it brings me to another element of my group. And then here, maybe I'd have to say another rule to make this make sense, because if I do 2 plus 3, 5 isn't an element of my group, but maybe I can kind of cycle back to previous numbers. And so 2 plus 3 would be like plus 1, plus 2, plus 3. And then so I could say like 2 plus 3 would be 1 for this group. And then the name for this group would be, I think, Z4. Z for integers, and 4 to just mean that I have 4 elements right here. And this group is actually cyclic. A cyclic group means that we have some element, maybe more than one element, that when we compose it with itself, we will get the whole group. So here, if I just have this 1, and I just keep adding 1, I'll get 2, and then bring this here. I'll keep adding 1, I'll get 3, bring this here. I'll keep adding 1. And then again, this isn't 4, but we're cycling back down to 0. And then I could bring this one here, and then add the 1. And then I'm now back to 1. And so all of the elements in my group are represented by just repeatedly applying the same operation to this 1. And this 1 is called my generator. Or in other words, this group is generated by the number 1. We could also express the same idea, like the exact same group, thinking about it with multiplication as our operator instead. I think this one I'm going to call Z5 and then a little star here. The 5 represents the idea that I'm going to cycle back down on 5 instead of 4. So like here, 4 and 0 were essentially the same thing. But for this group, I'm going to call 5 and 0 essentially the same thing. And then this star right here is kind of like that multiplication star, just saying that our operation is multiplication instead. But I want to put just these 4 numbers here, and I want to show that these two groups are essentially the same. Let's start with our identity element. The identity, again, is one that kind of does nothing, and then multiplying by 1 does nothing. And then let's test to see if 2 is our generator or is a generator. I could multiply by 2. I could multiply by 2 again. I could multiply by 2 again. Here, this is the number 8, but cycling it back down by 5, I do get 3. Multiplying by 2 again, I get 6. But then again, cycling it down by 5, I get the number 1. And so all of my numbers, all of my elements are represented. So 2 is a generator here, and I am thinking about it with multiplication instead of addition. But these two groups, I think, are exactly the same. One thing that we could do to like test this out is that, so 2 is a generator, and we saw that 1 is a generator. I think 3 and 3 are both going to be generators as well. Maybe you could try that out yourself. But I think 2 is going to be not a generator in our first group, right? Because if we start with the identity, add 2, we get 2. Add 2 again, we're going to get back to 0. And then if we try that again with the number 4 in our group with multiplication, 1 times 4 is 4, then 4 times 4 is 16, but cycling that down by 5s, we do get back to 1, which is our identity element. And so here, it looks like 1 and 2 and 3 and 3 are kind of like the same kind of element in these groups. And then 2 and 4 are the same kind of element in these groups as well. And then finally, 0 and 1 kind of share the same role as that identity or that do nothing number. And for the problem today, they're using exponents to represent repeated operations here, like this exponent of 715. And so I think it'll be a bit more valuable to think about our groups with multiplication, just because that's what the current problem is doing today. So we have a cyclic group of order 4004. So imagine this, but instead of 4 elements, we have 4004 elements, and it's generated by A. So A could be kind of any element, not really sure, I guess not that 4. Some kind of element where if we repeatedly multiply by A, we're going to get all the elements in our group. And so we could represent something like 1 for our identity, A for the generator, and then like A squared, A cubed, A to the 4th, all the way up to A to the power of 4003, I think, because this one right here is kind of like our A to the 0, and then there are going to be 4004 elements here. And then let's make sure that we have our operator in our group as well. It's just going to be multiplication. So we have our group now. There are 4004 elements, and we need to find the order of A to the power of 715. The order of an element is just how many successive operations on it that we need to do to get back to our identity. So like here, the order of the element 2 is 4, because it took 4 steps to get back to our identity 1. But then the order of this element 4 was 2, because it only took 2 steps to get back to our identity 1. And so here we need to figure out, okay, A to the power of 715, we need to compose it itself over and over and over again until we get back to our identity. And so we're not really sure how many times we're going to compose A to the power of 715 with itself, but eventually we are going to get something that's congruent or kind of equal to the identity element. This could be A to the power of 0. This could also be A to the power of 4004 if we want, because again, if we tried applying another A, we didn't have an element here, we would cycle back down to our identity. So I'm noticing that we can use some exponent rules right here, right? We are just kind of doing repeated multiplication of a bunch of A's. And so we do have A to the power of 715 raised to some power, right? We're not really sure how many times we're going to compose this A to the power of 715 to itself. I mean, technically we do, because supposedly this is the number 28, but we don't know that yet. So I'm just going to say maybe R for like order, perhaps. And I'm hoping that we can show that this R needs to be 28 for today. Okay, and this is supposedly going to be equal to A, or congruent rather, to A to the power of 0 or 4004. Essentially, we could have any integer multiple of 4004 and it would be fine. So I'm also going to do 4004 and then raise that to some other power, maybe K. And ideally, these two things actually could be equal to each other. We could just figure out when these exponents are equal. Let's do a little exponent rule. 715R is equal to 4004K. And then I think it would be useful here to see if there are any common factors. Let's see, 4004 looks like 4 times 1001. And I believe 1001 is divisible by 11, right? Because let's see, 11 could go into like 990. And then, yeah, if we add another 11 to this, we are going to get 1001. Looks like we have 111 here, and then we have 90 11s there. So this 1001 is equal to 91 times 11. And then I know 91 because earlier in this year, I thought 91 was prime, and it's not. 91 is the same thing as 7 times 13. So now we're going to have the full prime factorization of 4004, still times this k. Let's do something similar to the 715. Maybe let's just divide it by that 5 to see what happens. Oops, that's supposed to be a 5. That was supposed to be a 2. Drop the 1. There's a 4. Just more long division. Okay, 143. So we have 5 times 143 times r. And then I think 143 is also divisible by 11, right? Because if we do like 13 plus 130, then we would get 143. So this shows me that 143 is 11 times 13. Cool. Times the 5 times the r. Got it. Let's see if we have any common factors on both sides. And we do. There's an 11. There's a 13. And then that's all we got here. So we have 5r is equal to 28k. And there are no more common factors. So the first time that this will be actually true, the first time that these are equal to each other, is when r is 28 and k is 5. And this is what we wanted to prove. We wanted to prove that when we have 28 compositions of 8 to the power of 715, we do get to some multiple of 4004. And that will be the identity element of our group. And so we've done it. This 28 is our answer. That shows that once we compose this element to itself 28 times, we will get back to our identity. And that is the definition of what it means to have the order of some element. So R is just the order of 8 to the power of 715. That's 28. And we're all done. So there is my solution. Hope you enjoyed. I'll see you tomorrow. Bye.